Hello, everyone. Thank you for joining this session. My name is Gautaman, and I have my colleague Rajat joining with me for this webinar series on concept modeling. Basically, we want to explore all the features pertaining to concept modeling using morphing with the help of Zero CAD. With that being said, let's move on to the next slide. So we first want to understand who we are. So DEP stands for Detroit Engineered Products. We are founded in 1998, and we have four arms: the consultancy arm, the software development, and we are basically the creator of the MeshWorks platform, the product development, and talent acquisitions. We have an in-house R&D as well as the R&Ds are located globally. We are headquartered in Troy and having offices in various geographies like India, China, Japan, and Canada. And we have distributors across Europe and many other countries. So if you look at the DEP team, so we are about 550 plus engineers, and we are situated in various other geographies. We have about multiple offices in Chennai, and we have our headquarters in Troy, Michigan. And the blue color represents our distributors in various other geographies. And this is DEP's customer partial list. So you can see that this is just a partial list of our customers. And looking at our journey, as you can see, we established in 1998 and we started our operations in Chennai in 2000, launched the MeshWorks platform in 2001. And from then onwards, every alternate year, we either create a new arm or we are able to open new offices in various other geographies. And with that being said, let's quickly jump into today's presentation on MeshWorks. So first of all, what is DEP MeshWorks? So DEP MeshWorks is a CA platform which can work on all the sorts of pre-processing, which can handle all sorts of meshing activities and connections activities, as well as the post-processing capabilities. Since we do handle pre and post, we have a highly automated workflows where you can create your automated workflows to bring in efficiency to the table. And we have the concept modeling tool, which is going to be on today's webinar, where we can generate FE models without the help of CAD data, as well as the morphing tools. With the concept modeling and the morphing tool comes the parameterization capabilities, where you can parameterize your CAE models for optimization and pushing to the next one, which is the time-saving MDO. And we have two new modules, which is the innovative raw module and electrification module, which will have a subsequent separate webinar on these topics. And finally, the AML capabilities, which will also be on a separate topic. And the first one, what we would like to address is MeshWorks is a tool that can be applied in all the stages of your product development lifecycle. So this is a very cool graph that shows the current trend versus the new trend. The current trend is pushing the CAE as much as possible in the detailed validation phase, and the new trend is pushing the CAE even before the CAD team, that is during the conceptual stage. So this is the stage where you can do all sorts of morphing, like what you see on the left-hand side. If you have an existing FE data, you can morph the data to match the new design, use cut and stitch methodology to create a crossover, or use concept modeling tools to create new bill of materials. So this is where MeshWorks shines, and this is the bread and butter of our DP platform. And when it comes to the detailed phase, since we are into the pre and the post processing, MeshWorks can handle all the sorts of meshing activities as well. And during the virtual validation and the maintenance phase also, we can start using MeshWorks. And since we are focusing more into the morphing and concept modeling, let's for now go over the conventional CAE processes. So the conventional CAE process is to start with the CAD design, and from the CAD design we get a CAE model, out of which we build different domain models like crash, NVH, CFD, and solve them to see if the targets are met. If the targets are not met, then we go over multiple iterations, which are design iterations. And this is done by, again, talking with the CAD design team, doing the necessary modification in the CAD data, and coming through, again, the process of CA modeling, submitting the run, and verifying whether the targets are met. And once the targets are met, now we freeze the design. So in using DEP MeshWorks, you can now use the transformed CAE processes where you can start your CAE model, which is either generated from a CAD model, or it can be a concept model that is derived through morphing, like the one you see on the right-hand screen. And the same process goes on. You can do the morphing of the crash model, NVH model, CFD model, and check whether these are meeting your targets. And if they are not meeting the targets, then you can build a parametric CAE model where you can do all these kinds of morphing or parameterization. So on the right-hand side bottom screen, you can see the parametric CAE changes, and along with that, we also see the cross-section of the model and how it's changing. So this way you can build n number of parameters, not only just the shape parameters, you can also build gauge, bulkheads, beads, doublers, and so on. And from the parametric CAE, you can generate multiple design models to see if you can generate a DOE model, and from there on do an optimization. Since we are now talking about multiple domain models, the parametric CAE technology in MeshWorks can handle MDO kind of scenarios. And the next step is, once we freeze the CAE design, the next one is to finally deliver the CAD model for doing various other studies like the packaging, cost estimation, manufacturing kind of simulations, for which the CAD is the starting point. So once we have the optimal FE model using the original CAD data, the original FE data, and the optimal FE data, we can do the CAD morphing, impose the changes from the original CAD, the original FE, and the optimized FE, and finally get your CAD as well. So in this way, you completely avoid the CAD interface, thus saving you a lot of time. So hundreds of iterations of designs are also possible in a week when we use the HPC cluster modes. And now let's talk about the ConceptWorks. If you have data to start with, yes, you can use the morphing capabilities. But what if you do not have data to start with? So that's where we start with the ConceptWorks technology. So what is ConceptWorks? So ConceptWorks is our patented DEP technology, wherein you can build a body-in-white model without any CAD data. So since the CAD data, since the ConceptWorks eliminates the need of CAD, it's going to be very quick and cost efficient for you. In this presentation, we will illustrate two workflows. One is from an STL data, how do we get a body in white? And second one, once you have a body in white, but you do a topology optimization for various other load cases, and if you want to add new bill of materials to your models to accommodate the topology results, how do we do that? So let's talk about these two workflows using ConceptWorks. So here we are taking a body in white upper body, and we are planning to create all the members and joints using very few inputs. So what you're seeing on the screen is a body side outer, and the roofs are actually derived from the STL data. With the BSO and the STL data as a reference, let's see how quickly it is possible to create the other parts of the body in white. So in this case, we are using a cross section as a reference to build our A-pillar members. And here you can see that by doing a couple of clicks on the BSO, we are able to create our own trajectories. So this trajectory is useful because most of the members are of non-uniform cross sections, and this will help you in creating all these sorts of members. And let's talk about another example of building on top of this A pillar that we just created, which is the B pillar outer. And again, using the cross section as a reference, we are trying to use multiple points on the screen to create our own trajectories. So with this, we are able to quickly generate the other models also. And we'll just look at one more example of how easy it is to create a roof and roof bow, and then connect the roof bow to the neighboring regions. Because one of the most critical part is just not creating the members, but integrating the members to its surrounding regions. So you can see how easy it was to create the members. And now, again, with a few clicks of a button and very minimal inputs, we can see how this roof bow gets integrated to our surrounding. This is our joint creation process. So in the interest of time, I'll just skip some examples and I will walk you over another scenario where, in case if you already have a body in white, but we are trying to create some new bill of materials based on the topology results. Now let's take a look at that example. So this is the front end structure member creation using topology results. So what you're seeing on the, let me just pause the video for a second. So what you're seeing on the screen, the red color resembles the topology results, and you can see that the topology results are actually determining a member to be extended till the front region. So we are using the ConceptWorks tools to extract the section and then create a trajectory and integrate them to the surroundings. So this way, without going back to the CAD engineers, you're able to create these members very quickly. And this is another example where it's a very highly curved region where the topology results have determined that there needs to be a member connected in this particular region. So using the multiple cross sections as inputs, we are able to create the member and then connect them to the environment. Yeah. And so the next one is going to be, okay, if you have cross-section information? Yes, so for that also we'll be able to quickly generate concept members. So we also have planned some live demos on all these steps that we have. So we can see that once you have all the critical cross sections for your studies, so we can start building all these members. Once you have the members ready, then you can start creating these joints based out of these members. And our joint creation function, which we call it as an auto joint, can handle different kinds of scenarios like a T-junction joint, angle joint, straight joint, and so on. So these are all the examples where we were able to create these members and the joints using just section information. And once you have the body side outer, the previous example shows you how we can build the remaining parts of the model using the ConceptWorks tools. And this is another example of using ConceptWorks to generate a gigacast model. As you can see, we have the important informations like the mounting points, the body, outer line, BSO lines, the rocker sections, and most importantly, the packaging space. So that when we create our members, we will be able to make sure that the members that we create do not have any sort of interference with the design space or the body opening lines. So now we can see how easy it is to, with these inputs, we are going to derive all these kinds of stamp members. So initially, we will be planning to create these stamp members. And once these members are generated, we can go ahead and integrate them to form a kind of a casting. And on top of that, based on the mounting parts, mounting locations, we can go ahead and integrate the bosses and so on. And once you have a single component, now in order to improve the stiffness and to imply the casting features, we can go ahead and start creating the ribs and the bosses to connect to them. So this way we can achieve in creating these kinds of conceptual design using ConceptWorks very fastly without the help of CAD data. And with this, I'll move on to the next slide. So what is next? So right now we can see that we have generated a mid-plane mesh which can be used for the crash model, but this model can be quickly converted into a solid model which can be used for all your durability purposes. And this is actually a tetra mesh model. And once you have the concept gigacast ready, so we can also use the MeshWorks parameters to create all the sorts of parameters like this. In the case of a shell rib parameters, but in the case of a tet model, you can see that the tetra rib also can be created as one of the parameters. So let me just fast forward this video so you can see the tetra rib that's been generated. And these are some of the feature parameters where you can create tetra ribs, bosses, and so on. On top of that, we will also be able to create some shape parameters. If you want to do any sort of iterations to understand which region to concentrate more on stiffness, or if you want to use the same model for a different platform like a CUV or a crossover, instead of doing everything from scratch, you can use our morphing technology and parameterization technology to take care of this multi-model capability. And next one, this is an example of showing how easy it is to create a boss inside MeshWorks. So once we have the gigacast ready, and when you want to integrate bosses and with the bosses stiffen the component using ribs and so on. So this is a boss feature that we have. Now let's see how we can quickly generate a boss out of this 1D feature. So the user just selects a couple of inputs and he has the capability to reposition these features on any plane of the geometry. And once that is done, we can go into the inputs. So we have the ability to see whether you can use the feature to fuse, cut, and so on. You can also go into the detail of even providing a draft angle for the bosses in order to consider the manufacturing constraints. So once you have given all these sorts of inputs, the boss gets created in a much faster way. And the second one, let's see if we want to create the second boss. And now that we have two bosses where you can see the fuse and the cut difference, you can now go ahead and create your tetra rib based out of these two inputs. So let's go, let me just quickly fast forward a video where I can show the creation of tetra rib along with the fillets. So this way, these kinds of concept features can be quickly tried out, iterated, and you can pretty much get the results in a very, very fast way instead of going through the regular approach of doing everything in the CAD-based approach. Okay. And the next one is our advanced morphing capability. So when we look at the advanced morphing, gone are the days where the user needs to learn about the creation of control nodes, morph set creation, where you want to define the deformable nodes and so on. So as a user, you can select the component that you are interested in morphing. The feature lines are extracted based on the inputs, and the deformable nodes are all automatically set by the tool. So now you can treat this feature lines like a clay model where you can pull and push the feature lines however you require, and the tool automatically takes care of the deformable zone and morphs the model for you. So at this point in time, you can see that only the 1D gets morphed in the first instance. So this is an example where we are seeing the change in 1D. And once this is acceptable, you can go ahead and say update mesh. At this point in time, the 2D mesh gets updated. So we have also introduced various other morphing like gliding, fillet radius change morphing on the 1D level, and smoothing. Everything has been integrated as a part of the transformation functions. So this is another example where you can just pick a curve, change the curvature, and be done with the morphing. The precision of morphing, since we work on the curve level, the precision of the morphing is very, very high. And the auto quality robot can also handle these sorts of part stack up. It's going to check for the intersections that happens during the morphing and automatically removes them while doing the remeshing and the reconnections. There are also other ways you can establish creating a concept vehicle. One is taking a sedan model and an SUV model and creating a crossover model using cut and stitch methodologies, which are all the different methods we use inside MeshWorks to generate concept models. So with this introduction, I'll stop here and I'll leave the floor to Rajat for some of the demos that we have planned today.
Yeah, thank you, Gautaman. Hi everyone. I'll be showing demos on showing various demos on different capabilities of MeshWorks. So first we'll start with design space creation. So this is a cut section of a full vehicle model, and here our intention is to fill out the gap between these two components that you can see over here. So we have a special tool over here, which is called as body structure design space interior. So it will create a design space between these two components. So we'll start by defining the boundary. First, we'll select the two components. Then we'll select the node at which boundary will be created. And then we'll define the vector plane. Similarly, we'll create the boundaries for other locations. Define the vector plane. And again, repeating the same process at the final last location. So the boundary has been defined. So next we'll create a tet mesh between these intersection lines. So this tet mesh will be created using the offset method. So here we can define the offset, how much offset we want. So I'm sticking with 0.5 and simply click on create tria mesh. So this step would produce a tria mesh between the boundaries that we have previously defined. Next, we will adjust. We'll make sure that the boundaries are completely enveloping the two components, and it's on the location where we want. So we can do this by using other options like create sidewall, create closed mesh, and modification tools to achieve a fully enclosed region of tria mesh. This would take about a minute to generate the tria mesh. It has generated the tria mesh. So you can see the final tria mesh output here. So in the interest of time, I have already created a tria mesh enclosing the two components. The pink color component that you can see, it's a tria mesh that is covering the gap between the two components. So next, we'll use the tetra creation option to generate the tetra. All we have to do is click on this component, click on create tetra, and it will create a tetra elements between it will create the tetra elements between these two components. Along with creating the tetra elements, it will also create RB connections between the two components. Again, it has generated the final tetra mesh output. I'll hide the 2D mesh so you can look at the tetra elements, autocolor it, and you can see the final tet mesh output along with the RB3s that are generated for giving connections to the components. So next, I'll move on to, for the next demo, I'll move on to ConceptWorks. So here we have a sidewall component, and here we have a component, and we will be creating various structures using ConceptWorks. So here I'll be showing how we can easily create a member, quick fillets, or quickly create fillets, or a bead using ConceptWorks. So we have this ConceptWorks option over here, and here we have multiple options. We can quickly create fillets, holes, splits. We can do feature inserts, quick beads, boss creation, etc. So for now, I'm going to show you how we can generate a member with zero CAD and with minimal inputs. So we'll go to predefined member. So first, I'll show you what members we can create. So we can create multiple types of members. These are the 4 different types of members that we can create using this option. I'll go to predefined member, and first we'll start with creating a trajectory. So all we have to do is go to click create trajectory. I'll hide the 2D mesh and click on the nodes. So I've already previously generated the nodes for creating the trajectory. And then I click on create. So it has created a trajectory for generating the member. Click on return. Next, we'll proceed with creating the member. So we'll give this CAD curve as our trajectory. Next, I'll define the height axis for the member by giving 2 points as the input. Then I'll select the base component, and then I'll give the basic geometry inputs like the member height, member width, and flange width and draft angle, and the element size and the fillet radius. So the basic geometry inputs, and click on execute. It will take about a few seconds to generate the member. It has generated the member. So you can clearly see it is tracking the position of the base component. So we can see beads over here. It has tracked the position of the beads as well. So in this way, by simply giving a trajectory, a CAD curve as a trajectory, and giving basic geometry details, we can quickly create a member using ConceptWorks. Next, I'll show you how we can give connections or create a joint between these two components. So I'll click on return. So we have the standard joint options to create a joint between between the components. So we can create multiple different types of joints, like the joint over member, or the sidewall joint, or the end caps, etc. So for this example, I'm going to just show sidewall joint, but we have this multiple options. You have to go to standard joints. I'll go with the sidewall joint, and then first we'll define the cross section by giving nodes as the input. Then we'll define the vector for the joint and the connecting part. For the flange, we'll then define the top section, left section, and the right section by giving the nodes as the input. So I'm now defining the top section. Next, I'll define the left section. And the right section. And we can even provide the element size and the flange width. I'm just going to stick with the default values and simply click on execute. So using the cross-section data, the details of the cross-section over here, and the basic details about the flange, top, left, and the right sections, it will generate a, it will create a joint between the two components. Next, I'll show you how we can create a fillets quickly by simply selecting the nodes on this component. Just did auto color. We can go with the quick fillet option and simply select the nodes. Provide the fillet radius and the number of elements on the fillet edge, and click on execute. And it will generate a fillet in this area. So it has generated the fillets. Next, I'll be demonstrating how we can quickly create beads using a similar method by simply selecting the nodes and giving basic geometry details. So we have the quick bead option. All we have to do is define 2 points, give 2 points as the input between which the beads would be created. And then give basic geometry details like the width and the depth, and click on execute. It has generated the bead. We can even reverse the direction of the bead by clicking on reverse. It has reversed the direction of the bead. So similarly, we have multiple features. So we can, using a similar method and similar approach, we can even quickly create bosses, holes, or do a feature insert, BSO inner parts, using a same method. So next, for the next demo, I'll be showing how we can create a B-pillar member using these 1Ds. So we'll be creating a B-pillar using this 1Ds as the input, as I previously mentioned. So these 1Ds would be serving as the cross section for the creation of our B-pillar. And these 1Ds can be easily extracted using the styling data. So I'll be going with predefined member, multi-section member, and then selecting these 1Ds as my input to define the cross section for creating the B-pillar. Next, I'll be defining the nodes for defining the trajectory. And I'll click on create. So it will create a CAD curve to define the trajectory of trajectory. So using the cross-sectional data and the trajectory, we can create a member using this function. It has generated the B-pillar using the cross-sectional data and the trajectory. So we'll simply say accept, and that's it. So next, using a similar method, I'll be also creating another member in another location. So in the same way, I'll be selecting the selecting the 1Ds, selecting the nodes for defining trajectory, and click on create. So it will create a CAD curve, and then I'll say preview member, and it will finally generate the member using the same process. It has generated. It's giving a preview of the member. So if this section is acceptable, we can click on accept, and Yeah. So for the next demo, I'll be showing how we can create joints between different members. These joints, they are created using the multi-section member option. So we'll be creating a junction using the auto junction function in the ConceptWorks. We'll be creating a junction between these joints, and we can create multiple different types of junctions. We can create a straight one, or between two members at an angle, or even a T-junction joint. So as T-junction joint is a bit complicated, I'll be showing how we can create T-junction joint using the auto joint functions in the ConceptWorks. So we can go to ConceptWorks, click on auto joint, and first we'll be defining a pair. We'll be creating pairs. So these pairs would we'll be creating trajectories between these two pairs, and I'll be showing you how. So first I'll be selecting the component, and then the nodes. And similarly I'll be selecting another component and nodes for creating a pair. So we have to make sure while selecting the nodes that the number of nodes are same, and the red color node indicates a starting point for creating the pair. So this indicates a starting point for this particular component, and this, so we can select correspondingly, we can select this particular node as my starting point. Click on pair option, and you can see it's assigning the same color to the both of the components, showing that it has been paired. Similarly, I'll be creating different pairs at other two locations as well. And I'll be creating the pair finally at this location using the same process. So you can see the pairs have been assigned the same color. And when I click on preview, it will create trajectories between the paired components. So once these CAD curves are defined, we can go ahead and create the geometry. So we also have the option for modifying the curves. We can click on a particular CAD curve and do some slight modifications by dragging the curve if you want to. But right now, as the trajectory looks good, we are just going to proceed and click on create. So it will create a member between the joints. You can see the final output. It has nicely created the joint between the members. So next I'll be showing feature-based morphing for my next demo. So in case of, if you want to do quick morphing changes, feature-based morphing is the best option. All we have to do is select a few feature lines to do feature-based morphing. So it's like we call it clay morphing. It's like playing around with the clay. So I'll be going with the advanced morphing option. Here I'll be going with feature-based morphing, and it's a very quick way of doing the morphing. We don't need to define any control nodes or a deformable nodes or anything. All we need to do is just define the feature angle, select the displayed elements as the input, and then click on create. So it will automatically create the morph set, and we don't have to define any control zones or deformable zones or fixed nodes. So actually, next we can click on transform option to do the transformation, and we can do the transformation simply by selecting the 1D feature lines. I'm doing so I'm selecting the 1D feature lines for doing the transformation, and simply click on translate option, and it's showing the control nodes, and I'll define I'll be doing the translation on along the y-axis. Click on translate, and you can see the 1Ds are moving right now. 1Ds have translated. Say accept, and then I'll update the mesh. So as you can see, the mesh has been updated. Similarly, we can even do a line fillet change using this particular option. So I'll select the 1D feature lines. Click on line fillet change and select create CAD curve. It will automatically identify the fillet using this option. And it is already, all we have to do is now select the point, define the radius, and click on execute. So it has changed the fillet radius. Now I can click on update mesh, and it will accordingly update the mesh. Next, I'll be showing clay morphing on a component level. I hope you're able to see my screen. So I'll quickly, I already previously created parameters for this function. So I have in this particular component, we have already extracted the 1D elements, and we'll be changing the dimensions of these 1D elements to morph the component. So all we have to do is create the parameters, and I'll be doing parametric changes on this 1Ds, which represents the cross section for this component. So I'm changing the width and the height of the particular component. And then we have the map function over here. I simply click on link, and you can see how the 2D mesh maps to the 1D elements and gets morphed. The 2D mesh has also got updated. Hide the control nodes and the deformable nodes. So with this, this concludes my this finishes off my demos. I'll be handing the stage over to Gautaman to finally conclude the session.
Thanks, Rajat, for the nice demos that you have shown so far. So let me quickly jump back to the presentation. And one of these demos that we want to show is also on the CAD morphing. So this is an example of a casting component where you can see that we have the optimized FE model and the original FE model. So the optimized FE model is having very less wall thickness and some rib changes, profile changes, which in order to reduce the weight and still meet the baseline performance. So with these two FE models, now we can see how we can do the updates on the CAD side. Okay, so this is the difference that is showing not only the rib profile but also the wall thickness. So our CAD morpher environment is used to load the CAD model, which is the baseline CAD model, and then set up the parameters. Now we can define the baseline mesh model as well as the optimized FE model. So with this, the tool will understand what is the changes that is happening on the FE level and do the necessary changes on the CAD model. This way, you can get the updated CAD model so that you can share it to your suppliers for doing all the kinds of manufacturing feasibility analysis. And this way we conclude from start to finish how without the help of the CAD we can do all these kinds of concept modeling and even going to the extent of delivering the CAD data as a final result. So I would like to end my session here with the important points. MeshWorks is a game-changing CA platform that can transform your CA development lifecycle, accelerate your processes. Thereby, you can see a significant time reduction, automate your workflows so that your tedious and repetitive tasks are reduced. And we also have innovative modules like the eMod and the ROM to help you quickly reach your product goals in a very short period of time. Thanks everyone for joining this session. Have a great day.
Thank you, everyone.